Now that we understand what partitioning, let's discuss how it can actually be useful for the sorting problem. So let's suppose we have an array of numbers, in this case 5, 3, 2, 1, 7, 8, 4, 6. One way to sort would be to first partition on some pivot, let's say the leftmost item 5. And as you guys know, that means getting 5 into a location where everything to the left of it is less than or equal to, and everything to the right is greater than or equal to. Where you can think of these as the red items, 3, 2, 1, 4, and 7, 8, 6 as the blue items. So how is this useful for sorting? I mean, if we look at it, a bunch of stuff moved around, but it is not sorted. So what do we do? Well, I'm going to make a couple of really important observations, and actually, maybe to avoid spoilers. So if you're somebody who thinks, I want to try and relive the dream, I'm going to try and be Tony Hoare circa 1960 and make this happen, pause and think about it. Okay, so the two key observations that are handy are, one, well, while the array is not sorted, 5 is. Okay, 5 is in its place. It's exactly where it would be if the array were sorted. Now that might seem kind of strange. What does it mean that 5 alone is sorted? How can you sort one thing? Well, one way to think about it is there are no inversions involving 5. Everybody's happy with respect to 5. Or another way of thinking about it is that everything that is less than or equal to 5 is on the left, and everything that is greater than or equal to 5 is on the right. So there's no need for 5 to move, right? 5 could just stay there, close its eyes, and wait. Let the rest of everything get sorted, and 5 knows it's good to go. Now, another really important point is that we can actually sort the two halves totally separately at this point. 5 actually acts as a wall, that if we were to sort the left side with merge sort or insertion sort or selection sort or heap sort or whatever else, that we wouldn't need to think about the items on the other side. 5 is a barrier across which none of the items would ever need to move in order to get the array into sorted order. Okay, great. Well, one thing that's really cool about this is that rather than using merge sort or selection sort or something, we can actually just recursively partition. So to get a flavor of how that works before we do a full demo, let's imagine what that might look like. So 5 is a wall, and then we want to sort this left-hand side. So what we could do is partition on the leftmost item on the left side, in this case 3, and end up with 2, 1, 3, 4. And then on the right-hand side, we had 7. Okay, and what does 7 do after we partition? Well, it moves to its appropriate place. So at this point, after doing 3 partitions, we have 3 items that are in guaranteed good position. And so if we were to repeat this process so that every item got its chance to be the pivot, by the end of that process, the whole array will be in sorted order. So let's see a more thorough example, in case you didn't fully buy that, and get a sense of what this will look like. So I'm going to start with the recursive leap of faith demo, where we're just going to assume it works and see how it looks, and then we'll go through in grueling detail how everything behaves. So how Quicksort works, or you might also call it partition sort, is we start by partitioning on the leftmost item, in this case 32. Here I'm actually going to color everything explicitly red or blue to mean less than or equal to or greater than or equal to respectively. And so when we partition on 32, in this case it ends up second from the right. We have a bunch of items that are less than or equal to, and one item that is greater than or equal to. At this point, 32 is sorted, and then we just need to sort the left half and the right half. Now, if we take the recursive leap of faith that this is going to work out, that means after we do the left-hand side, all of these items are in sorted order, they're in their place, and then after we do the right-hand side, well, it's also in its place. And we end up with this tree, which I'm going to generate soon. Okay. So now let's see in a little more detail. If you don't really fully trust the recursion, if the recursive leap of faith didn't feel right to you, well, this is the video or the sub-video for you to enjoy. So again, we start with 32. This is the very verbose version of the same demo we just saw. 32 ends up in its place. And now when we do the left-hand side, I'm actually going to unroll the recursion and show every single step. Okay. So in this case, 15 ends up being the new pivot. And so after pivoting, we end up with a 2 on the right and a bunch of blue items, 2 on the left and a bunch of blue items on the right. And we have now completed the partitioning on 15 process. And now we have 2 subproblems we need to consider. So what I have up here in the top right corner of the slide is just a tree of all the partition calls. So partition 32 had a subproblem on the left that's of size, or that's called partition 15, that was size 1 less, 2 less than the original problem. It had 1, 2, 3, 4, 5, 6, 7 items instead of 9. And so after we finish this process of partitioning, we have 2 subproblems. On the left, we have this tiny problem of size 1. And so in this case, I'll show it explicitly, and we say, let's partition this tiny item, or this array of size 1 with 2 as its pivot. And so trivially, it doesn't move, and it's in its place, and it has two size 0 subproblems. And so I'm just going to mark those with an X. Okay, so now we're done with partitioning on 2, so we go back up to 15, and we need to do the right-hand problem. So in this case, I pick 17, and I pivot, we partition with 17 as a pivot. And in my case, just arbitrarily, I've decided that these other 17s should be blue. But it actually doesn't matter if I assign the color red or blue, they'll both still work just fine. So in this case, I just arbitrarily decided that greater than or equal to items will stay over there. And so in this case, after the partitioning process is done, 17 does not move. Oops, I went backwards there. 17 does not move. It is in its place, and the left subproblem is of size 0, so there's nothing to do. On the right-hand side, we still have 4 items to consider. In this case, 19 will be the new partitioning element, or the pivot. And I'm just, every time, always doing the leftmost item. So when 19 is my pivot, after partitioning, we have two 17s on the left and a 26 on the right. Okay, so that's partition 19 is done. We go to the left, and 17 is our new pivot. I'm going to speed up a little because it's probably getting a little tedious, even at 2x speed. And so when we partition on 17, it does not move, and its left subproblem, you'll observe, is nothing. So I put an X, and then we do the right subproblem, which is just 17 with two size 0 subproblems. Now we go back up to 19. So we go back up, we got to finish our much earlier recursive call, and in this case, we have to do the right half of 19. What's the right half of 19? Well, it's 26. So we partition on 26, nothing happens. We have two subproblems of size 0. Then we go all the way back to the unfinished business of partitioning, or going back to item 32 as the pivot. So we now have finished quicksorting the entire left half, which we did the recursive leap of faith at the beginning of this video. Now we did it in full detail. And so now we just need to do the right half, which will be 41. So 41, trivially, there's no work to do. The two subproblems are of size 0, and so we'll just put some X's there. And so now we're done. That is Quicksort. Now I'm going to make a quick little observation I'll return to in a bit, which is if you look at the tree of calls, it looks kind of like a binary search tree, which I think is kind of interesting. And so we'll return to that in a bit. So that is the algorithm that is known as Quicksort today, but maybe it could have been called partition sort instead. And so from now on, now that we hopefully have a good grasp of it, we'll start doing some analysis of its runtime and some of its other properties.